This here is all the data of the charging process of a 6S battery pack. And yes, it's refreshing in real time, unlike my bank account every time that I buy some tools that I don't need. So I've made this powerful and homemade solar BMS system, and I want to show you how to make one. And yeah, it's fully open source. Nothing says more that I'm an engineer than building something that could turn your garage into a supernova. Make sure that you have this with you. Solar BMSs of 50 or 100 amps could get quite expensive, forcing you to choose between safety and making groceries. So maybe a homemade version would be a better option, if you prefer the budget before maybe burning your house down. This PCB is for a 6S battery pack, but it could be changed for less than that. It could also work maybe up to 100 amps or at least 50. It has an output for a fan control so it could cool it down, an OLED display, push buttons, Wi-Fi, so you can send the data with a LAN server and see the data in real time on your smartphone or a PC. I have the BMS there on the table charging. We can set the current limit, we can see the pack voltage, how much capacity it's charged up, the current is getting lower and lower, we can see the voltage over time which is getting up, the current over time which is getting lower. We can change to minutes or hours, so it's been like maybe half an hour, and yeah, we can see each cell separately, and we also have buttons to turn the charging on or the discharge on or off. So let's see how to make one, how it works, and more important, let's learn something new. Remember that this channel is for learning and having fun, not for making perfect products or PCBs. What? So let's see how to make one. Before I try charging these batteries with a simple wire, make a short circuit and end this video early. By the way, this will not be a solar battery pack, this is just for testing. To start this project, you'll need the design of my PCB and a lot of free time. So get the Gerber files from below for free. And then you go to PCBWay.com and click the Code Now button. And you add the size, the amount, and select a solder mask color. Select green color if you like tradition, black if you don't want to see the smoke if you miswire the PCB, or red if you don't want to see the heat from the MOSFETs. I've selected this one. Then you save to cart, and then you upload the Gerber files that you have downloaded from my website and make the order. It's that easy in just a couple of minutes to order from PCBWay and save you from the DIY version and get professional PCBs. I just received the PCBs and they look awesome. No missing traces, no short circuits, just professional manufactured PCBs. We can now start. So again, go below to the tutorial page and also download the schematic for this tutorial and the code, also for free. So maybe support me on Patreon. Support my work to prevent me from going on a diet of eating only flax. Okay, so if you check the schematic, you can see that we have 6 blocks with optocouplers and MOSFETs. So we avoid the high voltage to go to the ESP32. And these optocouplers will act as a digital firewall, because the ESP32 is like a little chip that will always cry if it sees something bigger than 3.3 volts. So these MOSFETs will act as loads when a certain battery, a certain cell is already full. As you can see on the PCB, these tracks are exposed. So we can fill them with solder till they look like a silver mountain. So they could handle a lot more current without turning into a space heater. As you can see, I've designed my board in Altium and I've tried to use thick tracks so they could handle the current, but sometimes that is not enough. So for example, for these tracks here, I've exposed the copper. In order to do that in Altium, select the track that you want to expose, Ctrl C to copy that, and then you go to Edit, you go to Paste Special, paste it, and you paste it where you want it to be. Select it once again, and from top layer you change it to Paste, which will be this one, Top Paste. And now this will be exposed, so we can add a lot of solder, so it could withstand a lot more current. When the PCB is ready, I go to Rules and I run the Design Rule Check. And if everything is okay, I export the Gerbers, go to Fabrication Output and select Gerber files. Generate the Gerbers that you want, and then export them. My PCB has a lot of parts: optocouplers, MOSFET, a screen, a fan for the MOSFETs, the ESP32 buttons, a buck converter, current sensor, an output for the batteries, an RJ11 because why not, and also an RGB LED because any PCB should have one. So let's assemble it. A little bit of theory for those who skip the physics class to just play video games. This kind of BMS will use the ESP32 ADCs to measure the voltage on each cell. If one voltage of one cell is already at 4.2 volts, it will stop the current going to that battery just by using a MOSFET as a bypass. So it turns on the MOSFET, the current passes through the MOSFET, turning the current into heat without charging the battery, So the rest of the batteries will get charged, but the 4.2 volts one will not. That's how it will work. So when the batteries are full, the code will just stop. And the code also has some extra stuff to create a server, so we can see the real data here on our phone for the current, the temperature, the power, the milliamps, and so on. We'll see more about this in just a moment. Okay, so let's assemble the PCB, and you have the full part list, the schematic, and everything that you need on the website electrums.com, which by the way has a new update. It has a very cool new design, so go and check it out, maybe you like it, and in that way you maybe won't see the errors that I have in my code. Okay, I first soldered the optocouplers. We need 6 of them right here. I have the optocouplers, I'll add the resistors for the optocouplers, and then I solder the MOSFETs on the back. I've soldered here the transistors, and you'll see that I've used through-hole power resistors instead of SMD because the one that I've ordered are not the value that I needed. So yeah, for this prototype I'm using this kind of resistors. In a moment we'll solder this current module, but before we do that, since this will go here on top, we have to fill the tracks with solder so they would withstand more current. So before you adding the module, make sure that you fill this with solder. Now I get the buck converter, and using the small potentiometer I fix the output to 5 volts. Don't skip that step because otherwise you will burn your board. Then we can solder it right here. Okay, so finally we add all the peripherals. I've added the screen, the push buttons there, the module, have the ESP, the RGB LED, also the connector for the fan and the buzzer. So now the PCB is ready. I still have to connect the thermistor on this pin here to measure the temperature and also add some sort of heat dissipator on top of the MOSFETs together with the fan, in case this will waste too much power and get too hot. Okay, now that the PCB is ready, it's time for the code. So let's go to the PC and get ready for some classic unoptimized C++ copy pasting. The code has actually two parts. One is the web.h, which is basically the code for the website that we're creating on the server, and the other one is the firmware, which will make the calculations and send the data to that server. Actually creates the server. In the code for the website, we print the values that we receive from the ESP32, and we also create this graph, this canvas. And then as you can see, each 1000 milliseconds we update the chart with the values. We have the IT for current, WT for power, we have the milliamps, the temperature. All this data are coming from the ESP32, updated in real time to the chart. And the ESP right now is charging, and as you can see, this is the website in real time. We can set the limit for the current, we have the voltage of the pack, we have the ramp here for the voltage, and as it's getting up, we have the current which should be going downwards, we have the minutes, the hours, and how much charge we have, and some buttons to control it. And the best of all, it has this retro old terminal from an old computer look with the CSS, and I think it looks pretty good. The ESP will store this data to the RAM, not to the flash, avoiding the flash from dying, because if you save each 1 second something to the flash, in just a few days the memory might die. So in this way, if you refresh the website, you still get the data because the ESP32 still has that data. And then here in the code, with this handle data API, we send that data to the server. As you can see, we're sending the total, the current, the milliamps, the temperature, everything is this JSON, and each time the website will connect to the server, we'll get this data. Also, please comment below if you think it's interesting to make a tutorial on how to make this kind of communication between the ESP32 and any IP with a website and send data back and forth. As you can see, this is like a tiny IoT system, but it's locally, it's on a LAN server. This function, for example, haggle toggle output, is coming from that push button, from this one here, the discharge, and since we have a main switch on the PCB, a main MOSFET, each time that I press this, I can just cut off the switch and no current will go to the output. Pretty easy. After we define all the variables, this is the void loop. We check if we are connected to the LAN and if we are in a safe mode, because we can detect an overcurrent, overvoltage, and so on. If we are not, we don't have problem with safe mode, then we just run a few functions. read the voltage, read the current, read the temperature, and handle the balancing charging, which is basically turning on and off those optocouplers if one battery reaches 4.2 volts. And that's it. It's not a very complicated code. You have it below, upload it to your ESP and start making tests. So let's upload the code and hope that the compiler won't throw a tantrum. So the code is uploaded and it will tell you the IP where you have to go. We go to that IP, so we have the values here, but as you can see everything is zero, both on the OLED display and on the website. And that's because there is no battery pack connected to the PCB. Without that we can get voltages. So yeah, let's just do that. We need to connect these pins from B0 to B6 to the battery. Also the main B plus and B minus. This BMS is for a 6S battery pack, so from 0 to 25 volts. Now this is a very small pack just for testing. Actually this could work with a lot bigger batteries because it could output a lot of current. So we need to connect all these pins here from B0, which will be the most negative part of the battery, till B6, which will be the most positive part of the battery. And everything in between, we have to connect them to the battery cells. On a normal BMS, the P plus and B plus pads are internally connected, so they are the same pin. Then the P minus pin is a separate part of the circuit controlled by switches, and the B minus pin represents the main ground of the PCB, connected to the battery. So connect the pack like in this schematic. Since the PCB has its own buck converter, it will get those 25 volts and transform that to 5 volts connected to the ESP, which has a 3.3 volts regulator. So that's how we feed the power to the entire board. I have connected color-coded wires so I don't get them mixed, and I will connect them to the battery pack. Okay, now the PCB is connected to the battery and now we do have all the cell values. The problem is that these batteries are quite charged up. It's almost 23 point something volts, so the batteries are almost full. And if I connect my power supply, there is very low current passing through. So let me just discharge the batteries a little bit, connect them to some load, and then make a charge test. But you can see we have in real time the value for the voltage, for the current, which right now is 0, and if we change to minute, well, the voltage is always the same because it's not connected to anything. Okay, let's empty a little bit the battery. Okay, I've emptied a little bit the batteries. As you can see here on the screen, 3.9, 3.9. The batteries are almost at the same voltage. But as you can see, we still have 0, 0, 0 because this is not charging. Let me connect the power supply. Okay, now the supply is connected and the battery is charging. And we can see here, pack voltage is going up. The current is 1.7 amps because the battery pack is almost charged up. And we can see the graph here. Now, till you don't get to pass this line here, you won't see the difference because the scale is from 0 to 25. We can also see the current, which is actually, you can see that is dropping. It was 1.8 something, now it's 1.7. So let's just wait till this line gets here so we can see the voltage in real time, but we can also see the milliamps that are charged to the battery. Only 29 milliamps till now. So there you go. This is the line that you would expect to get. The voltage is going up and the current is going down, as you can see here, and that's it. It's charging. So we should wait till one of the cells gets to 4.2 and then we'll see that one of these LEDs will turn on. I think the C6 is the most close to, no, C5 is 4.06. Let's just wait to get to 4.2 and see the LED. So as you can see, 4.19. So at any point now, one of the LEDs will turn on, meaning that one of the optocouplers is turned on, meaning that that battery pack, that battery cell is fully, there you go. There you go. C5 just turned on, and that battery, which is this one here, is fully loaded, is fully charged. So now the power is wasted through the battery, through the resistor. By the way, I can also come here to my PC and I have the same website just by going to the IP. And we can see the current, we can change to minutes, it's only been like 5 minutes. We can change to hours, we don't have anything, but we can get the values here, as you can see. And if I reload the page, I still get the values because these values are directly from the ESP and they are stored into the RAM. It's been a while and pretty much all the optocouplers are turned on, so we have only one battery that is not charged, and this pack should be ready. Another test we could do is to test the output current limit. So as you can see, I'm connecting this load and nothing happens. because this load weighs around 10 amps. Let me just go to the smartphone here and change from 15 amps the current limit to, let's just say, 6 amps. Now the current limit is detected by this sensor here and is detected both for charging and discharging since it's the same port. And now if I touch the same pads, look what happens. As you can see, it turned red and there is no output. As you can see, I'm touching, the output won't turn on and it beeps. Now I've made some calculation with the AI and this should be rated with these MOSFETs for around 50 to 100 amps. Now I know that's a huge difference, but now we would need a lot more heatsink than this one. Now some MOSFETs that I've used are rated up to 200 amps, especially the main kill switch. The other ones don't need to waste that much power. The IRF Z44N is enough for this job because it will only make like a bypass for the battery. But yeah, we still need a lot of heatsink, so maybe this small block and this fan is not enough. I will improve that in the future. But for now the tests are working quite well. Now I will be sincere, I have made some errors. You might have seen some jump wires here and that's because I've used pin 17 as an analog input for the current module, and 17 is not an analog input, so I had to cut some pads on the board and then make the connection with the wire. So yeah, my mistake. I will correct that on the final schematic. Another mistake that I've made, well, it's not actually a mistake, but it's something that I would like to do in the future, is not to use the ADC of the ESP32. Now the ADC is quite good, it has a good resolution of 12 bits, but using an external ADC like the 1115, the ADS, that gives you the ability to measure directly the difference between each cell, because in this case I'm measuring the difference between ground and cell 1, 2, 3 and 4 and then you subtract the values and then you get the real values. It's not like actually measuring the cell. That would be an improvement. And I would like to add screw holes for the fan because I don't have right now, so I'm not sure how to connect it. I would also like to make it more compact, and also maybe it would be awesome to add a bus boost converter at the output and not just stop the charging process when we have an overcurrent, but control the current for the charging process and the discharging process. That would be like a bigger PCB than this one, but it would be awesome. So guys, this is still a prototype, maybe wait for another better version if you want to make this. But if you want to buy a BMS from AliExpress, for example, for 50 or 60 amps, it will cost you more than $60. But nowadays you can buy an ESP32 with like $4 and the PCB will cost you like $10 to $15. So yeah, maybe a homemade version will be better and you have fun and learn something, as I did. So you have everything that you need below in the description. Just don't blame me if something blows up. You have the PCB, the code, the schematic and everything on electrons.com. Oh, and I think that one of the best parts of this PCB is learn how to show everything on a LAN server, create a LAN server with this ESP and see it from your mobile phone, see the values from your PC or from everything around your house if you have a Wi-Fi connection. That's pretty cool and easy to do. So I hope that you like my project and that it will help you learn something new. If so, maybe comment below or give me a like. That will push my videos a lot and I need that nowadays. And if not, maybe you want to support me on Patreon. The links are below. Thanks again and keep up, you guys.